Swayam Prabha. Digital India. Educated India.
Okay, so I've used the term naive, of course, right? So that's giving you a hint that there are some issues with this. So this looks almost equivalent to proof of work. And what we are going to have is that we can set this threshold so that every so often you will have a block generated, maybe every 10 minutes or every 1 minute or whatever, right? And these blocks are generated randomly in the network. You don't know in advance who is going to win the game, right? So it's something very similar to proof of work, where you have participants all around the internet and somebody or the other generates a block every so often. Right? So you could still have forks over here. It's possible that two people at roughly the same time generate blocks, in which case we have the original problem and we have to decide how to resolve these forks. Right? And we could say that, okay, somebody choose a particular block to mine on, each miner, and let's say the longest chain wins. Okay, so we could think of some sort of a protocol like that, right? But there's no such thing as a free lunch, right? So this seems to have solved the problem. So we're not using up a whole lot of energy. We are just using the stake that people already have on the blockchain in order to decide who is going to create the next block. Okay, but there are issues. And proof of stake can be very subtle, and it could be very dangerous to use it if you don't know what you're doing. Okay, so let's look at some of the issues. And one of the issues is something called the nothing at stake problem. So it's a pun on the word stake. Right? So nothing at stake is an English phrase, right? You have nothing to lose, right? Nothing at stake to lose. So let's say that you have a proof of stake blockchain using this naive protocol that I mentioned, and it so happens that two people at roughly the same time generate blocks, right? And you have a fork, and now you want to resolve this fork. So Satoshi was using proof of work, and he said that any miner can choose one of these, right? And he said that you choose the first of these which you saw. Okay? And one of the things with proof of work is you cannot use your computational power multiple times on multiple blocks, right? So you're trying to evaluate a hash function, and so you have some sort of an algorithm running, and in proof of work, you have the hash of the header, and you want this to be less than the threshold. Okay. So you can put only any one of these two headers into your hash function, right, and evaluate it. And so somebody would be mining either on this block or he would mine on this block typically, right? You can't mine on both the blocks. But in this naive proof of stake protocol, there's nothing to stop anybody from trying to extend both the chains, because it's not a computationally difficult problem. He could try to solve this problem, what I've shown over here, right? So this, maybe he runs this 1,000 times, right? He can choose 1,000 different timestamps or whatever, 7,000 or whatever. And he does it on the top block and he does it on the bottom block also, right? He can do that pretty fast. And he can try to extend both of them. Now this is the nothing at stake problem, because every miner, he doesn't know which chain is going to be finally accepted. So he can try to create blocks on both the forks, both the branches, right? So what would happen eventually is that there's nothing to lose, there's nothing at stake for people. So you might have forks here, and all of these chains keep getting extended. And instead of having a single chain, you have a tree, which is really confusing people. They don't know which particular chain is going to win out, right? And there's no such, they don't know which is going to be the longest one or whatever. So everybody keeps extending all the chains. And that is because the problem to be solved is not computationally heavy. Everybody can solve the puzzle for all of these chains. Right? So you cannot resolve forks very easily with this naive proof of stake protocol. Right? So this is one issue. Right? And it's called the nothing at stake problem, that everyone mines on, or everyone extends every branch in the chain. Yes.
How are we guaranteeing that the problem we are solving with hash will be lesser than the threshold? We have 1,000 values.
Yes. Yes. So let's look at it over time. So let's say this was the last block which was generated, and it was generated at this point in time. So the question is, a question is about this whole mining process, right? And so right now you can, suppose we are currently here, this is the present time. There's only a certain number of timestamps that I can use, right? And everybody in the network is trying to do that with their own account numbers and balances. And let's say nobody is able to solve the problem. That could be possible because the threshold is too small. So then the time progresses, and you can use a certain set of timestamps here, right? So suppose we have reached this point in time. So people can use timestamps in this range, and maybe one of these solves the problem, right? And then the next block is generated here, right? And then they broadcast the block, right? So it's very similar to proof of work in that sense, this particular protocol. Right? Okay, so this is one problem, but there are other issues. So something called a long range attack. So this is, let's say, my blockchain. Let's say there are thousands and thousands of blocks. And suppose this is Satoshi's blockchain. So consider a proof of work blockchain. Suppose somebody wanted to launch an attack such that he went back in time, let's say to the early days of the Bitcoin, right, 2011 or whatever. He looked at a block there and he tried to create a chain which is longer than the current Bitcoin chain, but he wanted to do it privately. So this is all private to the user, right? So some sort of an attacker wants to do this. So he wants to go back in time. This is the public Bitcoin blockchain at the top. And this person wants to create a blockchain privately which is longer than the public one and then release it. And Satoshi's rule says use the longest chain. So that would kill this public chain. And that would be the end of Bitcoin, because everybody's Bitcoin is no longer accepted. There is this new chain which is longer, in which probably the attacker has a lot of the Bitcoin or whatever, right? But if somebody could launch this sort of an attack, it would be devastating to Bitcoin. Right? But in proof of work, it's very, very difficult for anybody to do this, because to generate a block, you need to expend some amount of energy. You need to have some amount of computational power. And creating this many blocks in private, you would have to, it would be possible, but you'd have to invest billions of dollars in hardware, right? Which only a government, let's say the US government, might be able to afford to do, right? But smaller people, like you and me, we cannot throw in that kind of money. So we cannot create this sort of a private chain ourselves, which is very long. Right? So that way Bitcoin is secure. The energy being used in the network is making it more and more secure. Right? And in fact, the more energy expended, the more secure the network is. Right? So can we perform this sort of a long range attack with proof of stake? Okay? Using our naive proof of stake protocol. So let's say this is the present time, we have a very long chain and the attacker wants to go back in time, right? Right, and so let's say this is, let's say that I'm looking at time and I want to see how long it's going to take for the attacker to generate his private chain. Okay. So let's say he has 10% of the stake in the network, right? And let's say that here, let's say you have to wait for 10 minutes, roughly on average, to create a block. And let's say that the attacker has 10% of the stake in this blockchain at this point in time, right? So roughly it's going to take him 10 times, so it might take him 100 minutes to generate a block here, right? So this is all happening in private. So this 100 minutes really corresponds to the timestamps that he has to use. It doesn't really take him 100 minutes in real time. He just has to try timestamps starting from the timestamp in this block and keep increasing it, up to maybe when he increases the timestamp by 100 minutes, he is able to create a block, right? And then what he does is he gains some amount of stake because he gets some mining fees. As you learned, there's a coin-based transaction, right, to reward the miner. So his stake goes up. Let's say it goes up, let's say it becomes 11% over here, right? And now he has 11% in order to invest in this mining. So now it might take him, let's say 95 minutes on average to generate a block, right? Okay. And again, this is not 95 minutes in real time. He just has to try out timestamps, pushing it forward by 95, and then he solves the puzzle, right? And he keeps doing this and creates a lot of these, and very fast he's able to create these blocks. And maybe after some time, since he's got all the coin-based transactions in this chain at the bottom, maybe his stake goes up to whatever 60 or 70%, right? Or let's say even 90%, right? Because everything that has been generated, all the coins generated from this point in time onwards are now with the attacker. And by the time he creates a blockchain which is almost the same length as the original public blockchain, he might have most of the stake and he might be able to actually generate a longer chain, okay, with some reasonable amount of probability, right? And in fact, his timestamps over here might be something similar to the timestamps used in the public blockchain, okay, just the way that this has worked. Of course, here there's a big gap of 100 minutes, but then the gap is reducing and his timestamp here might actually be close to the real time. Now if he releases this chain, people will be forced to accept it because everything seems to be fine. He's followed all the rules, he solved all the puzzles appropriately, and this chain is longer than the public one, okay? So since it's easy to generate these blocks, you don't need computational effort, this sort of a long range attack is possible. Okay, so there are other attacks also, but maybe in the interest of time I'm going to skip over them. There's something called a pre-computation attack. Where somebody can actually try to create blocks even in the future, okay, if he knows that he's created a current block, okay. So there's some sort of tricks in order to do that, okay. So there's something called a bribe attack, which is related to the nothing at stake problem, where if you have a fork like this, or suppose you have a chain like this, okay, you could incentivize people. Maybe somebody launches an attack and he can tell people that I want you to extend this lower chain, and if you extend this lower chain, I'll actually pay you some ether or whatever the coin is, right? And it doesn't cost people to try to extend this chain, so they might actually fall for the bribe. Okay. So there are various attacks like this in this naive proof of stake protocol. So people were thinking of better proof of stake protocols, and one of the ideas is to combine proof of work and proof of stake. Okay. So let's look at a simple way to do that. So suppose I have a blockchain and I say that every n blocks I need to have a proof of work block, and let's say the rest of them n minus 1 are generated by proof of stake. Okay. So this is how is this better than proof of work? Well, it's not using up as much energy. So suppose you have the same thresholds, let's say for proof of work, right? People will only switch on their hardware and use the hardware to perform proof of work. They will run that hardware only when they need to generate this nth block, and for the rest of the time they will switch off that hardware. Okay, so in theory you're using a small fraction of the original energy that you were using. Okay, so it's better than proof of work in that sense, right? And you're using proof of stake, let's say a naive proof of stake protocol for the rest of the blocks. Okay, so does this solve the, let's say, the nothing at stake problem? Okay, we've talked about nothing at stake. So suppose a fork occurs over here. Okay, so all of these are generated by proof of stake. So maybe the chain will extend like this. You might have a nothing of stake problem where both chains are extended. But this doesn't continue indefinitely, because then somebody has to generate a proof of work block which can only be done on one of them. So one of them wins, let's say that it's created on this lower chain, and now this chain gets extended. Right? So the nothing at stake problem will occur, but not for too many blocks, at most for these n minus 1 blocks, and then the forks get resolved by the proof of work block which is generated over here. Okay. So what about a long range attack? Can I launch a long range attack from here and create a private chain which is much longer, let's say, than the original chain? And now again we have to deal with this proof of work blocks. I will have to, every n blocks, use proof of work to create a block. And it's non-trivial for me to do that. I would have to expend a lot of energy. I would have to buy a lot of hardware. Right? So it would be easier than maybe doing it on Satoshi's chain, because there every block is using proof of work. But here every nth block. Okay, so it's maybe not as hard, but it's not so easy like a long range attack on this naive proof of stake protocol. Right? Because every, let's say, nth block would still need me to expend energy, which is non-trivial for me to do, right? Okay, so this is one solution that people have thought about. So people were also wondering, can I use both proof of work and proof of stake on the same block? So can I have a block, let's say, which has some proof of work, maybe a low amount of proof of work, but also have some sort of proof of stake on the same block? And one of the persons thinking about that was somebody called Vitalik Buterin, who is one of the founders of Ethereum. Okay, so Vitalik Buterin was like you guys, right? Doing his bachelor's at that time, and he got something called a Thiel Fellowship, founded by Peter Thiel. So you guys can also apply for a Thiel Fellowship, right? But this is a very controversial fellowship in the sense that if an undergrad, somebody in college has a very good idea for a startup, Peter Thiel will pay you to leave your studies and do the startup, right? Because his idea is that time matters a lot. You can't wait 5 years for your idea to mature. It may be too late, right? But lots of people disagree with that because it's sort of encouraging people to leave their academics, right? But Buterin took the fellowship and he started Ethereum, right? But Buterin had lots of ideas. He was thinking of how to shift Ethereum to proof of stake. And one of his ideas was something called Slasher. I just want to talk about it briefly. And of course, the current Ethereum does use proof of stake, but it's an advanced version of Slasher. Okay? So Slasher uses both proof of work and proof of stake. But the proof of work used is very low compared to Bitcoin. So what Buterin proposed is that you reduce the mining fees very fast over time. So Satoshi says that you halve the mining fees every 4 years. Right? That's what he said. So right now I think if you create a Bitcoin block, you get 6.25 Bitcoin, right? So Buterin said you do that every few months, let's say, or you do it much faster, right? So that people are less and less incentivized to do this proof of work, right? If they get very little mining fees, right? But there is a little bit of proof of work, at least in this Slasher protocol, right? But can we come up with a better way to do proof of stake than this naive method, right? So suppose we have these blocks being generated by proof of work, right? And the notation I am going to use is that this is a block with proof of work, but if I draw a circle around it, it means that it also has some sort of proof of stake. Okay, we'll have to see how exactly that is done. Okay. So if I just have a proof of work blockchain which has very little proof of work done, okay, somebody can launch all sorts of attacks like long range attack and whatnot, right? Because he doesn't have to invest much in the hardware, right? So how do we prevent things like nothing at stake or long range attack? Okay. So what Buterin suggested is that you have people who vote on blocks based on some sort of stake that they have. So you have some sort of a committee right? And so what he says is that suppose I have a fork which is created here, which might happen. Okay? Now I want to resolve this fork based on votes. Okay? So what he says is for this particular block, let's say that this is, I am calling the blocks B0, B1 and so on, and this is, let's say, BK. I will form a committee and I want to do that before this block is even created. So somewhere over here I form a committee which is going to vote in order to decide what is going to be the block at the kth position. Okay? So what Buterin says is that suppose I call this committee some CK, right? So he says that if 2/3 of the people sign a particular block, they would have to cast a vote saying that I am willing to accept this block, then it is accepted. Okay. So first somebody generates a block using proof of work, so that may or may not get into the blockchain finally. Let's say 2 of them happen to be generated. Right? Let's say that these are already signed. Okay. And 2/3 of the people sign on this lower block, then this is accepted. Right? Okay, so it's different from what we had earlier. We are not really solving a puzzle as such, right? As long as there are enough votes supporting a block, then it gets in. Okay, something like voting in parliament or voting in elections, right? And let's say that we go on here. Let's say there was only one block created here, and let's say the committee for this one, let's say the entire committee casts votes. They broadcast these votes, accepting this. Right, then the block is accepted, and then you have proof of work, let's say, and then people cast votes, right, and in order to decide which of these is actually accepted. Okay. So at a high level this is how it works, but the question is, how do you choose people in CK? So we have to have some sort of a mechanism, and Buterin's idea is to use stake. Okay. So depending on the amount of stake you have, you can get elected to this committee. Let's say that we want a committee of size 15, and we have something like this proof of stake puzzle that we had earlier, but we're going to use that to decide who is going to be in that committee CK. And let's say we choose 15 people, right? And now if 10 of those actually sign a block over here at this particular position, then that block is accepted, right? And as time progresses, we elect newer and newer committees for the various blocks. Okay. So you might say, is this going to work? I mean, what if 2/3 sign 2 blocks? Okay, so what if that happens? So why won't you have a situation where somebody signs this block and this block? Right? Suppose you have 15 people in the committee, and let's say all 15 even sign both the blocks. Right? It's something like a nothing at stake problem, right? I mean, so there has to be something at stake for the people. So Buterin said you fine these people, right? You punish them. Okay, so what he says is that if somebody with the same key is going to sign multiple blocks at a particular level, then no matter which of these gets extended, or suppose based on proof of work or whatever, one of these chains gets extended, in any of these chains anybody can give a proof of malicious behavior, okay, and you can show that somebody has signed with the same private key. Let's say that he has signed 2 different blocks at a particular level. You give that proof as a transaction and you punish him. Okay, so there is something called a punishment transaction, which you can put in the blockchain somewhere in the future in order to punish these people, right? So, but how do you punish them? Well, so there has to be a mechanism for that. So what he says is that you have to put a deposit over here. Anybody who wants to become a particular member of, let's say, CK, he has to first lock some amount, let's say some ether, in the blockchain, and that is going to be locked for a very long amount of time, much beyond this BK, even thousands of blocks beyond this, right? So if somebody is cheating, then this punishment transaction can confiscate the deposit. Of that particular attacker, right? So this is a clever scheme, but it's clearly getting very complicated. Proof of work was very simple. You just solve the puzzle and then you're done. The block is generated, everybody accepts it and moves on. Now you have to have people volunteering to belong to these committees. So they would have to lock some of their ether in some sort of a deposit scheme. That could be some sort of a smart contract, and that money is locked, they cannot use it elsewhere. Then they volunteer based on some puzzle which they solve, okay, based on the stake that they own and so on, and they can volunteer to belong to these committees. And let's say some of them, only let's say 15 of them get into CK, and when the time comes to create this block BK, these blocks are generated using a small amount of proof of work, but then they have to be signed by at least 2/3 of people in order to be valid, right? And if you assume that 2/3 of the people in CK are honest, then you can show that you can never have more than one block which is signed over here, right? There will be only one of them. But so essentially these proof of stake algorithms, these protocols assume that most of the people in these committees are actually honest, right? At least 2/3 are honest, and so the scheme works, right? And you have to have this sort of a punishment transaction, right? So very, very complicated scheme, and the more complicated you make the scheme, the more chances that it can be brought down with an attack, right? And I don't think anybody has proved that something like slasher is going to work 100% under certain conditions, right? Maybe right, but it's harder to prove that a more complicated protocol is robust to attacks than something simple like proof of work, right? So this is a little bit about slasher, and there is also something called Algorand, which was proposed by Professor Silvio Micali. He's a very famous computer scientist, which is a pure proof of stake protocol. There is no proof of work used at all. And here too you use committees. Okay. So suppose currently the Algorand chain has blocks up to this point. What they do is, depending on the stake that they have, they create a particular committee. Let's call it committee C1, consisting of a small group of participants. And this is used to do something called leader election. Right? So let's say 15 people are part of this committee, and they broadcast some values based on which one of them is elected the leader, and the leader proposes a block. Okay, so there is no such thing as putting a deposit or anything, unlike what Buterin had in Slasher. You don't have to do that in Algorand. Just depending on your stake at this particular point in time, you can join this committee, and if you are elected the leader, you propose a block, right? And if you proposed only one block, then everything is fine. That block gets added to the blockchain and we move on. But you have to take care of situations where the leader might be malicious and it might propose multiple blocks, right? So in that case, what you do is you have multiple committees, and they are going to decide. Suppose you propose more than one block, they will decide on one of them, and they will choose one of them to get into the blockchain, right? And so you may have several committees, right? And this hopefully doesn't get run too often, and that most leaders are honest, right? But in case you have malicious leaders, you have multiple committees getting elected, and they will choose on one of these proposed blocks of the leader, right? So Algorand interestingly claims that there are no forks, okay, under certain conditions, because these committees ensure that only one block is chosen over here, right? And there cannot be, if you assume that suppose 80% of the people are honest in the system, not number of people, but 80% of the stake is controlled by people who are honest, then you can never have forks over here in algorithm, right? Okay, so this is sort of like the state of the art in permissionless blockchains. Everybody wants to use proof of stake because proof of work uses up a lot of energy, right? And there are various protocols being proposed out there, right? So any questions about this? Yes, you have.
In this session, the committee and the members of the committee cast vote for the future law. But what if they cast like equal votes? If there are 14 members and 77 members cast votes for it?
So that's a good question. So we've talked about a situation where only one block is signed. We were saying most of the people are honest. And what if you have, well, let's say everybody is honest, but 50% sign this and 50% sign this? That is the question. Then what happens? So what Slasher says is that we don't have a valid block at this particular position in the chain right now, right? Because we said that 2/3 need to sign it. So what he suggested is that you can skip one position and you can generate bk plus 1 directly on bk minus 1. This is what Buterin suggested. And there are certain attacks possible with this, because even when there is a valid block, somebody might try to do this and create a block pointing to an older one, right? So what he said is that to discourage people from doing this, you have a very hard proof of work for this, which means that the threshold has to be small. If you want to generate a block not at this position, right? So maybe you mention in the block what is the position, right? K plus 1 will be mentioned here. And if you want to point to a block at position K, then the proof of work would have to be much more difficult. And then again, it's the same rules as before. We would have to have 2/3 of people signing here, right? So he makes it harder and harder to point to an older block and generate another block. So that was his solution. Yes.
Slasher is still vulnerable to bribery attacks, right?
So it will have some of the attacks that we had before with the naive proof of stake, but since there is some flavor of proof of work, you can't arbitrarily extend all the chains. Proof of work is going to mitigate that to some extent. Yes. But even the current Ethereum protocol has some of the ideas of Slasher, and it has these punishment transactions and so on, right? So if somebody tries to misbehave and sign multiple blocks at the same level, he can still be punished. Yes.
So why can't we have just a simple solution that always to have odd number of members in the committee, right? Like just volunteer to never have a space where there is equal distribution of the assembly.
Oh, okay. So the question is, why don't we choose an odd number of persons in the committee and then we use a majority vote, right? So we have to look at so if everybody is honest, then that should work out, right? But we have to look at situation. In a permissionless system, there is no guarantee that people are going to be honest. So somebody might sign multiple blocks. That could be an issue, right? Or somebody may not cast his vote at all, and that too could cause an issue.
Do we have a limit on the number of committee members or something?
So yes, so you don't want to have too many people voting, because somehow these votes also have to be recorded on the blockchain. So Buterin suggested around 15 people. So he said the way you elect these committees, you ensure that roughly 15 people are.
That's all right. So we have a majority vote.
Yeah, but you have to take care of malicious participants in the committee.
There is a punishment for them.
So the whole thing works together, right? Yeah. So okay. Yeah. So is your question, why do we need 2/3 rather than?
Majority would work. Why won't majority?
Let me think. So the thing is, if if you have this 2/3, you can show that if you have 2/3, so it depends on your model. So if you assume that, so the question is, so how many, the question is how many people are you going to assume in the committee are honest? Really, that's what it boils down to, right? And so if you assume that 2/3 are honest, then you can show that the scheme is going to work always. Even if the other 1/3 or less than 1/3 people double vote, you are never going to have two blocks which have more than 2/3 of the votes, right? But if you have just 50%, if you just say that I want 51% votes and that's enough, and let's say that only 51% are honest, then those 49% of people might vote for both the blocks, and then you'll have two blocks which are valid. Okay, so it boils down to what's called a threat model, and the question is what percentage, let's say some X percentage, are honest, right? So you have to assume that, and based on that you come up with a protocol which and you can prove that it works if less than X% are honest, right?
So where does this money go, the ones that is confiscated?
That's a very good question. Where does the confiscated money go? And one of the tricks here is that the attacker might punish himself, right? So suppose a naive scheme is that whoever punishes the attacker gets all the money, then the attacker could punish himself, right? And he'd collect the money and he wouldn't lose anything. So what you have to do is you have to have enough incentive. So one thing is you burn part of the money, which means that you transfer the money to some key which you know that people, or some public key for which you know people don't have the private key to. It's possible to do that. Let's say the 0 key or something like that, the 0 public key. You know that nobody has the private key corresponding to that. So you transfer a large part of that deposit to that key, right? Then you give some amount to the person who's punishing the attacker because he needs an incentive, right, to publish that transaction. And then you give a little bit of the money to the miner who includes this punishment transaction in his block, so that he has an incentive to include this punishment transaction, right? So that has to be done very cleverly, but you definitely need something like a burn of the money, just so that even if the attacker punishes himself, still he's burning some of his money, he's losing some of the money. Yeah, another question?
So in the long range attack, how does the chain which is started below have 90% of the stake till the time it is less than the...
Yeah, so that's the question is in the long range attack. I think, so here, so I'm assuming that in this system that every time somebody creates a block, he gets some mining fees, like in Bitcoin. So initially he started out with 10% of the stake, but then all the new coins which were generated were owned by the same miner. So it became, let's say, 11% in this first block. And so I'm assuming that, let's say, 80% of the coins which were generated were generated, let's say, after that point in time. So most of the stake is owned by the attacker now, by the end.
With the chain which was initially, the part is growing also, and till the time it is longer than the attacker's chain, until that time it has more stake than the attacker. So it should be 50% that time.
No. So what is going to happen over here is that only one of these two chains is going to survive. So each chain is separate. Each chain is consistent with itself. So in the lower chain, the attacker has 90% of the stake. In the upper chain, maybe he has very little, right? I mean, he had 10% initially, and maybe that 10% has reduced because more has been mined in the chain on the top, right? But the point is that in the lower chain, he has 90%. And once he releases this lower chain, the upper chain is discarded by everybody. They just throw away the blocks over there. So only the lower chain remains now, and he owns 90% of the stake.
And sir, the timestamp, how did it ensure that the lower chain is going at a longer, higher rate than the top chain?
So what we want is in this scheme that I discussed, so by the time the attacker releases his chain, he wants to have more blocks in his own chain, plus he wants to have a timestamp in his block which is somewhat close to the current real timestamp, by the real time, because if he releases a block which has a timestamp much in the past, then people may not accept that block, or if it has a timestamp much in the future, people may not accept it. Right? So he wants a timestamp somewhat related to the real timestamp that everybody is using right now. Okay. Yes.
So for this chain, but I could not get it as longer as the original one. So do I get to keep the stakes?
No, so the whole world, let's say, is looking at these chains, and let's say the rule is that they look at the longest chain. Right? So if the attacker's chain is smaller, I mean, even if he releases it, nobody is going to use it. Yeah.
I'm saying the stake. Since you said it was 10% of the stake, then it got 20.
No, so you have to look at only a single chain at a time. So if the public chain is the longer one, people don't really care what is there in the blocks in the lower chain.
Okay,
so it doesn't matter. I mean, he cannot spend that money in the chain on the top. Yeah. Yes.
If the above chain is discarded, then can the people make more blocks in it and increase the chain again?
Yes, so they could, and we'd have to think of a situation like this happening in real life, right? Even in the current Ethereum chain, if somebody generates a longer chain and it's clear that he is performing the attack, then it's possible that the honest people say that we will still focus on the chain on the top and we will try to extend it, right? But the protocol itself will not do that. They'll have to have some sort of a forum to meet and decide to do that.
POS, everyone extends every branch, right?
They are not supposed to, but they have nothing to lose. Yeah.
Possibility that it could be like a tree with branches of equal size, right?
Yes.
So how will now with POS and POW combined, how will POW decide which is the longer one?
No, now if you have a tree which also has proof of work, then you have to pick and choose. You cannot extend all the chains. So you will choose one of the blocks and you will do proof of work on it. And once it has a longer chain, then you cannot extend all the blocks on all the chains. You'd have to choose one of them.
But in proof of stake, it's allowed to choose more.
Yeah, so let's look at it. So suppose you have a situation like this, some sort of so this is what you're talking about, right? And so all of these have proof of work. So suppose you even have a situation like this. One of them is going to be extended, even if you have proof of stake, right? So this is a combination of them. So let's say proof of work is done here, and now everybody accepts this because it's the longest chain, and let's say it gets enough votes and people proceed with this. You cannot, nobody is going to be incentivized to do proof of work on these lower blocks because the one on top has already become longer. So when you use proof of work, the longest chain wins. Any other questions? So, okay, thanks. If you have any questions, you can also email me, right? You can find my email, or I'll just write it here. Okay, so thanks a lot. It was nice interacting with you, and I hope you have a nice workshop. I think it's going to last for 4-5 more days, right? 5 more. Thanks a lot.